The next question is, why do deserts cool down so quickly at night? To answer this question, I've drawn a diagram. On the left is what happens during the day. We have the sun shining radiation down onto the Earth. Here's the Earth's atmosphere, here's the Earth's surface. And on the right is the same thing at night. The only difference really in the diagrams is we have the sun in one and no sun in the other. During the day, radiation from the sun hits the Earth's atmosphere and surface. The main forms of radiation we need to concern ourselves with are light, UV, ultraviolet light, which is a high energy radiation compared to light, and infrared, which is a lower energy form of radiation compared to light and UV light. During the day, these forms of radiation and others hit the Earth's surface and atmosphere, and it can be absorbed. So the Earth's atmosphere and all the Earth's surface can absorb this radiation. When the radiation is absorbed, several things can happen, but the thing that we're mainly interested in at the moment is increase in vibration of the particles in the atmosphere or on the Earth's surface. At night, when there is no incident radiation upon the Earth's surface, the Earth's surface and atmosphere start to cool down. This means that kinetic energy is being lost, but the kinetic energy simply can't disappear. Instead, it gets released as infrared radiation. So if we have a particle on the Earth's surface that starts to cool down and releases its kinetic energy as infrared radiation, then this infrared radiation can either pass through the atmosphere and be lost to space, or it can be absorbed by some particle molecule within the Earth's atmosphere. If this occurs, then that particle increases in its vibrational kinetic energy. This means that it has gotten hotter. Two things can happen to this particle after it has absorbed infrared radiation. It can either release that infrared radiation a short while later in some random direction, and that infrared radiation can either be absorbed by some other particle in the atmosphere or be transmitted back down to the ground or pass into space and be lost. Alternatively, the particle can move a bit and then collide with another particle, transferring kinetic energy to it, causing its energy to increase, in other words, causing its temperature to increase. And then the same things can happen to this new particle. Either it can release that absorbed energy as infrared radiation, or it can move along and collide with some other particle in another collision. Now, this means that the rate at which the Earth's atmosphere cools down is dependent upon how many things in the atmosphere can absorb infrared radiation. The more things there are in the atmosphere that can absorb infrared radiation, the longer it will take the atmosphere to cool down, because the longer it will take for the kinetic energy to be dispersed into space via infrared radiation. There are two main components in the atmosphere that can absorb infrared radiation, and they are carbon dioxide and water. Carbon dioxide's concentration in the Earth's atmosphere is relatively low, and so it doesn't significantly stop or slow down the rate of release of infrared radiation into space. Water, on the other hand, does strongly influence the rate at which infrared radiation is released into space for two reasons. One, its concentration in the atmosphere can be relatively high, and two, because it can absorb a wide range of infrared wavelengths. However, in deserts, there is relatively little water in the Earth's atmosphere, and therefore that component which strongly absorbs infrared radiation that's naturally present in the atmosphere generally is not present in deserts, and so there is very little in the desert's atmosphere that can trap or slow down the release of infrared radiation at night. And so the infrared radiation is lost to space relatively quickly, which means that the kinetic energy, i.e. temperature, of the Earth's atmosphere and surface decrease rapidly.